Module 4, Lecture A, Linear and Binary. By the end of this lecture, you will be able to implement linear and binary search algorithms correctly in Python, compare the time complexity of linear and binary search and relate it to input size and ordering, and identify and avoid common implementation errors in binary search code. Linear search basics. Sequential scan mechanics. Linear search is like scanning a list of student names to find one specific name. You start at the beginning, compare each item to your target, and move through the list one by one. The search stops as soon as the target is found or when you reach the end of the list. This simple step-by-step method works even when the data is not sorted in any particular order. In a linear search, the program starts at the first element in a list and compares each element in order to the target value. If it finds a match, it returns the position of that element. If not, it moves on to the next one. This continues until a match is found or the end of the list is reached, which means the target is not present. The search treats every element the same and checks each exactly once, which keeps the logic simple to understand and implement. Linear search is like checking items one by one in an email inbox or along a library shelf when you cannot jump straight to what you want. You simply move through each element in order, without needing the data to be sorted. In programming, this means you examine every item in the list until you either find the target value or reach the end. If you reach the end without a match, you know the target is not present in the data. Python code. Sequential scan mechanics. This segment explains how a simple linear search works by scanning through a small list, one element at a time. At each step, the current list item is compared to the target value. The process continues sequentially until the target is found or the end of the list is reached. Finally, the result is reported by stating whether the target value was found and, if so, at which index position in the list. This script does not require any pip install commands because it only uses features from Python's standard library. In other words, it does not depend on any external packages. This makes the code simpler to run and more compatible across different systems. Users can execute the script right away without extra setup or installing additional dependencies. We define a linear search function that looks for a target value in a list. It takes two inputs, the list of data and the value we want to find. We start the search at the first position in the list by setting an index position to 0. From there, the function will check each element in the list one by one in order. The loop first checks whether the current index is still within the list, preventing any attempt to access elements outside its range. As long as the index is valid, it retrieves the element at that position. It then compares this element to the target value to determine if they are the same. This process repeats until either a match is found or the index moves beyond the list bounds. This line outputs a message to the console that shows the current index and the value being compared to the target. It lets you see each step of the linear search as it happens. By displaying which element is checked at each moment, It makes the search process easier to follow and understand. This part of the code compares each value in the list to the target value we want to find. When a value matches the target, we have successfully located it. At that moment, the code returns the current index position. Returning immediately stops the search, since there is no need to check the remaining elements once the target has been found. The code increases the index by 1, so the search moves to the next item in the list. This lets the loop continue checking each element in order. The process repeats until the target value is found or the loop reaches the end of the list. If the loop finishes without finding the target value, the function returns none. This means the value does not appear anywhere in the list. Returning none is a standard way to indicate that the search failed. It lets the code that called the function detect this situation and respond appropriately. We begin by creating a list of locker numbers, where each number represents a locker assigned to a student. The numbers are intentionally left unsorted to reflect how data often appears in real situations. This unsorted list will then be used to show how a linear search can locate a specific locker number within it. We set the value 199 as the target locker number we want to find in the list. This value represents the specific locker we are searching for. By defining this target, we give the linear search process a clear item to look for. The search can then compare each locker number in the list to this target value to determine whether it has been found. We use a linear search function on the list of locker numbers to look for a specific target locker. The function checks each locker in order until it either finds the target or reaches the end of the list. It returns the position where the target is found, and this position is stored in a variable called the found index. If the target locker number is not in the list, the found index is set to a value that indicates the search did not succeed. The code displays a message that tells you whether the target locker number was found in the list. It checks if the stored index value is not empty, which means the target was located. If it was found, the program prints a message saying it was found and includes the index position. If it was not found, the program prints a message saying it was not found in the list. This script shows how a linear search works on a list of locker numbers. It checks each locker one by one against a target number and prints each comparison as it goes. When it finds the target locker, it stops searching and returns the position where it was found. If the target is not in the list, it returns no result. The example ends by printing the index where the target locker number was located. Best, worst, average cases. When analyzing the time a linear search takes, we look at best, worst, and average cases based on where the target appears in the list. In the best case, the target is the first element, so the search finishes after a single comparison. This ideal situation is uncommon and usually not under your control, because it depends on how the data is arranged. Therefore, it is important that your implementation stops immediately once a match is found, so it does not waste time scanning the rest of the list. In the worst case for a linear search, the algorithm must check every element in the list before it can stop. This occurs when the target value is not present at all, or is located at the very end of the list. As a result, each item is compared one by one, and the total number of comparisons increases directly with the size of the list. This behavior shows how the algorithm's running time scales with the length of the data. In the average case for a linear search, the target value is equally likely to appear at any position in the list, or not be present at all. This means that if the value is in the list, you typically find it after checking about half of the elements. If the value is not there, the number of comparisons still increases as the list grows, but this behavior is less extreme than in the worst case. Understanding this helps explain why linear search feels reasonably fast on short lists, but noticeably slower as the list becomes larger. Python code: best, worst, average cases. Explain linear search by clearly showing its best, worst, and average cases, and how many comparisons are needed in each. Emphasize how the number of comparisons changes when the target is at the beginning, in the middle, near the end, or not present at all. Use simple visual or positional examples so beginners can intuitively connect each case to where the target appears in the list. This comment simply notes that the script does not require any extra installations. It reminds us that the code runs using only the standard Python library. This helps keep the program simple, easy to use, and free from external dependencies. Overall, it signals that the script is self-contained and ready to run as is. This function performs a linear search on a list while counting how many comparisons it makes. It begins with a comparison counter set to 0, then checks each element in the list one by one. For every element examined, it increases the counter by 1. If it finds the target value, it immediately returns the current count, showing how many checks were needed. If it reaches the end of the list without finding the target, it returns the total number of comparisons, which equals the length of the list, indicating the target was not found. We use a simple list of numbers, 10, 20, 30, 40, and 50, as a small collection of unsorted data items to study linear search. This list lets us see how the search behaves when the target value is at the beginning, in the middle, or at the end. It also shows what happens when the target is not in the list at all. With this setup, we can clearly illustrate the best case, worst case, average case, and missing item scenarios for linear search. To illustrate the best case for linear search, we choose a target value that is placed as the first element in the list. We then run the linear search function on this list and target, and it counts how many comparisons are needed to find the target. Because the target is at the very beginning, the function finds it immediately and returns a count of 1. This result represents the best case scenario for a linear search. We choose a target value that is the last element in the list, so the linear search must examine every item before finding it. Then we call the linear search function with this list and target. The function returns how many comparisons it makes, and we store that result. This tells us how many steps the algorithm takes in the worst-case scenario, when the target is at the very end of the list. To model a case where the target is not in the list, we choose a value like 999 that we know does not appear. We then run the linear search function on the list using this missing value as the target. The function scans through the entire list, counting each comparison until it confirms the target is absent. We store this count as the number of comparisons for the absent case, which shows how many checks are needed when the search fails to find the target. We set the target value to 30 to represent a typical average case where the target is near the middle of the list. Then we run the linear search function on the list using this target. As the function moves through the list, it counts how many comparisons it makes until it either finds the target or reaches the end. We store this count of comparisons so we can use it later in our analysis of the algorithm's performance. We first note the length of the list, which tells us how many elements might need to be checked in a linear search. Then we compare how many comparisons are needed in different situations. The best case when the target is at the first position, the average case when it is somewhere in the middle, and the worst case when it is at the last position. We also consider the absent case when the target is not in the list at all and every element must be checked. Together, these scenarios show how the number of comparisons in linear search can range from very few to checking the entire list. This script illustrates how linear search works by counting how many comparisons it takes to find a target value in a list. It shows the best case when the target is the first element and only one comparison is needed, and the worst case when the target is the last element and the number of comparisons equals the length of the list. It also covers the absent case, where the target is not in the list and the search still makes as many comparisons as the list length. The average case is approximated by choosing a middle element as the target, which requires more comparisons than the best case, but fewer than the worst. By printing the number of comparisons for each situation, the script helps you see how the target's position affects the efficiency of linear search. Searching unsorted data. When data is unsorted, linear search is a simple and reliable way to find an item. You start at the beginning and check each element one by one until you either find the target or reach the end. Because it does not rely on any particular order or structure in the data, it works even when items are stored randomly. This guarantees that you will either locate the item or be sure it is not present. In programming, data is often unsorted, such as user logs, chat histories, or sensor readings, and any existing order, like time order, may not help you find specific information. When you need to locate something like a particular error code in a list of messages, the order of the data is usually not useful. In these cases, linear search works well because it does not depend on sorting and simply checks each item in turn. This makes linear search a dependable method for searching any list-like structure, from small sets of options to large collections of unsorted data. In a linear search on unsorted data, you must examine each element in order and stop only when you find the target or reach the end of the data. You should clearly define what the search returns when the target is not found, such as a special value or a true or false result, and use this consistently. It is also important to test your search with cases where the target appears multiple times, appears once, or does not appear at all, so it behaves predictably with real, unstructured data. Python code, searching unsorted data. We will demonstrate linear search using everyday unsorted data to show how the algorithm works in a simple setting. In linear search, we check each item one by one to see if it matches the target value. Because we look through every element, the order of the data does not affect whether the search is correct. We will display the result of the search both when the target value is found and when it is missing from the data. This line is simply a placeholder comment indicating where you might add a command to install an external library if one were needed. In this particular script, only standard libraries are used, so no installation step is required. It serves as a reminder for future situations when additional libraries might be necessary. We begin with a list of integers that represent different error codes, such as common HTTP status values like 404, 500, and 200. These codes are deliberately left unsorted to show that their order does not matter for the technique we are about to use. This setup is designed to demonstrate a linear search, where we scan through each element in the list, one by one, to find a specific value. By working with an unsorted collection, we can focus on how linear search operates in a simple and clear way. A linear search on an unsorted list is a function that looks for a target value by checking each element in order. It goes through the list using both the index and the current value. Whenever it finds a value that matches the target, it immediately returns the index where that value appears. If it reaches the end of the list without finding a match, it returns a special result, such as none, to indicate that the target is not in the list. We choose a target value that we know is already in our unsorted list of error codes. In this example, we set the target to 500 so we can later search for that specific value. This setup lets us show how the linear search process works when the value we are looking for is actually present in the list. We set up a variable called the missing target and give it the value 999, a number that does not appear in our list of error codes. This deliberate choice lets us test how the linear search function behaves when the value we are looking for is not in the data. Using this setup, we can show that the function correctly signals an unsuccessful search by returning a special result, such as none. We use a linear search on an unsorted list of error codes to find where a specific value, in this case 500, appears. The linear search function goes through the list one element at a time and compares each value to the target. When it finds a match, it returns the position of that element in the list. This position, or index, is then stored in a variable that records where the existing target value was found. We run a linear search on a list of error codes to look for a target value that is not in the list. The search function is given the list and this missing target as inputs. Because the target does not appear in the list, the function returns a special value of none to indicate it was not found. This return value is then stored in a variable, so it can be used later in the program. We print the list of error codes to show that they are not in any particular order, which demonstrates that linear search does not depend on sorted data. This emphasizes that the search will still work correctly regardless of how the elements are arranged. Displaying the list also gives a clear reference that helps you interpret the search results that come next. We display a message showing where the target value of 500 was found in the list. This message reports the index where the target appears. which is stored in a variable that tracks the found position. By printing this information, we can confirm that the linear search function correctly located the target within the unsorted list. We display a message showing the result of searching for a target value that is not in the list. In this example, the missing target is 999, and the output reports that it was not found and that its index is none. This confirms that the search function correctly returns none when the target value does not appear in the list. This script demonstrates a linear search on an unsorted list of error codes, showing that the order of elements does not affect whether the search works correctly. The search function simply checks each item in the list until it finds the target value or reaches the end. In the example, it looks for two targets, one that is present, 500, and one that is not, 999. The existing value is found at index 2, while the missing value produces a result indicating it is not found. Printing the unsorted list reinforces that linear search does not depend on the data being sorted. Binary search essentials. Sorted input requirement. Binary search only works efficiently when the data is already sorted, such as in ascending order. With sorted data, each comparison to the middle element tells us whether we have found the target, or whether it must lie in the left or right half. If the target is greater than the middle, we can ignore the entire left half, and if it is smaller, we can ignore the right half. Repeating this halving process is what gives binary search its fast, logarithmic running time, which is no longer possible if the data is not sorted. Binary search is like looking for a book on a shelf where the titles are in order. You check the middle, decide if your book comes before or after, and ignore half the shelf each time, which makes the search very fast. In contrast, if the books are placed randomly, you have to check them one by one, similar to a linear search. This comparison shows that binary search only works efficiently when the data is sorted, while unsorted data forces you to use slower, linear scanning. Sorting data can be expensive at first, but it enables very fast binary searches afterward, especially as the dataset grows. While a single linear search might be cheaper than sorting once, a sorted collection allows many later searches to be done quickly, with search time increasing only slowly as the data size increases. This makes sorting especially valuable in systems with repeated queries, such as databases or digital dictionaries. However, if the data is not kept sorted, you lose this advantage and must fall back to slower linear search. Python code, sorted input requirement. Binary search only works when the data is sorted, because it repeatedly compares the target value to the middle element and decides to search only the left or right half based on order. If the list is not sorted, this elimination strategy breaks down, and binary search cannot reliably find the target. In contrast, linear search checks each element one by one and works on both sorted and unsorted lists, but usually takes more steps. On sorted lists, binary search is much faster than linear search because it cuts the search space in half each time, while linear search still scans through many elements. This shows how ordering directly affects the number of search steps and the overall time complexity of each method. This line is simply a placeholder comment suggesting that you may need to install a library for the script to work properly. It reflects the common practice of checking and installing required dependencies before running code, especially in environments where they might not already be available. In this particular script, no installation actually occurs, so the comment mainly serves as a reminder or instruction for possible future needs. The script starts by importing the time module so it can measure how long different operations take to run. By recording the start and end times of a search, it can calculate the total duration of that process. This timing information is then used to compare the performance of linear search and binary search. In this way, the code can show how efficient each search method is in practice. Linear search is a simple method for finding a target value in a list. The search function looks at each item in the list one by one and checks whether it matches the target. If it finds a match, it returns the position of that item. If it reaches the end of the list without finding the target, it returns -1 to indicate that the value is not in the list. Binary search works on a sorted list by repeatedly narrowing down the possible location of a target value. We start with left and right indices at the ends of the list and keep a counter of how many steps the search takes. In each loop, we increment the counter, find the middle index, and compare its value to the target. If the middle value matches, we return that index and the number of steps. If the middle value is less than the target, we move the left index just to the right of the middle. If it is greater, we move the right index just to the left. If the loop finishes without a match, we return -1 and the number of steps to indicate that the target was not found. We start by creating a sorted list of numbers that begins at 0 and increases by 5 each time, continuing up to but not including 1,000. This produces a sequence such as 0, 5, 10, and so on. We then copy this list and reverse the copy so the numbers run in descending order from 995 down to 0. With these two versions, one sorted and one reversed, we can compare how search algorithms perform on ordered versus unordered data. We choose a target value of 735 that appears in both the sorted and unsorted lists, so we can fairly compare linear and binary search. Using the same target in both lists lets us focus on how each search method behaves. This setup highlights that binary search depends on the data being sorted, while linear search does not. As a result, we can clearly see why having sorted data is crucial for using binary search effectively. To measure how long a linear search takes, we first record a precise start time using the performance counter from the time module. We then run the linear search on an unsorted list to look for a target value, which returns its index if found, or -1 if it is not present. After the search finishes, we record the time again and subtract the start time from this end time. The result is the total duration of the linear search in seconds, which we can use to compare its efficiency with other search methods. To measure how long a binary search takes, we first record the current time using a performance counter. We then run the binary search on a sorted list to find the target value, noting the index where it is found and how many steps the search required. After the search finishes, we record the time again. Finally, we subtract the start time from the end time to get the total duration of the binary search operation. If we try to run a binary search on an unsorted list, it will not work correctly. The search function may still return an index and a count of how many steps it took, but the index it reports for the target value will be wrong. This happens because binary search assumes the data is sorted, so it can safely discard half the remaining elements at each step. Without that ordering, its decisions about where to look next are unreliable, which shows that sorted input is essential for binary search to function properly. We compare search performance to show why binary search requires sorted data. First, we report the index and time for a linear search on an unsorted list. Then, we show the index, time, and number of steps for a binary search on the same data after it has been sorted, emphasizing its efficiency. Finally, we demonstrate that running binary search on the unsorted list returns an incorrect index, highlighting that the data must be sorted for binary search to work properly. This script compares linear search and binary search to show why binary search requires sorted data. It defines both methods, then searches for the same target value in a sorted list and in a reversed, unsorted version. Linear search successfully finds the target in the unsorted list but takes more steps. Binary search quickly finds the target in the sorted list with fewer steps, but fails on the unsorted list. The key conclusion is that linear search is slower but works on unsorted data, while binary search is faster but only works correctly when the input is sorted. Safe midpoint selection. In binary search, choosing the midpoint correctly is essential for both correctness and efficiency. The midpoint determines how the search interval is split and whether you continue searching to the left or right. A poor choice can cause you to skip the target, get stuck in an infinite loop, or even trigger overflow in some languages. Even though Python handles large integers safely, it is still important to understand safe midpoint selection, so the search space is reliably halved at each step and the algorithm keeps its logarithmic time complexity. Binary search works by repeatedly checking the middle of a sorted list and discarding half the remaining items each time, so the number of comparisons grows only logarithmically with the list size. This efficiency depends on choosing the midpoint correctly and updating the search boundaries carefully. If the midpoint calculation is flawed and repeats an index, the algorithm can loop or revisit the same region instead of shrinking the search space. Proper midpoint selection and boundary updates ensure that each step truly reduces the interval and preserves the expected logarithmic time complexity. In binary search, how you define the search interval boundaries, whether inclusive or half-open, directly affects correctness and performance. For inclusive intervals, you must choose a midpoint that lies strictly between the low and high indices, so you do not repeat a same midpoint. For half-open intervals, you must adjust the midpoint and boundaries so the interval always shrinks. This careful handling of midpoints and boundaries is essential in real-world searches over large datasets to keep logarithmic time complexity and avoid edge case failures, ensuring the search remains efficient and reliable as data grows. Python code, safe midpoint selection. In binary search, it is important to choose the midpoint in a way that avoids infinite loops and incorrect behavior. A naive midpoint formula can overflow or fail to move the search boundaries correctly, which may cause the algorithm to get stuck or return wrong results. A safer midpoint calculation prevents these issues while still keeping the number of steps proportional to the logarithm of the input size. By using the safe midpoint, we preserve the efficiency of binary search and ensure it behaves correctly even on large ranges. This comment explains that you do not need to run any pip install commands because the script only uses features that come with Python by default. In other words, it does not depend on any external libraries. As a result, the code is easier to run, requires no extra setup, and should work on any standard Python installation. This description explains a simple binary search function used to find a target value in a sorted list. It keeps track of a low and high index that mark the current search range, plus a counter for how many steps the search takes. In each loop, it increases the step counter, computes the midpoint between low and high, and compares the value there to the target. If the midpoint value matches the target, it returns the number of steps and the position where it was found. If the midpoint value is less than the target, it moves the low index up to narrow the search to the upper part of the list. Otherwise, it moves the high index down to search the lower part. If the loop finishes without a match, it returns the number of steps and an indication that the target was not found. We define a safe binary search function that looks for a target value in a sorted list while counting how many steps it takes. It keeps track of a low and high index that mark the current search range and repeatedly checks the middle position using a midpoint formula that avoids overflow. If the middle value equals the target, the function returns the step count and the index where it was found. If the middle value is less than the target, it moves the low index just above the midpoint. If it is greater, it moves the high index just below the midpoint. This process continues until the target is found or the range is empty, in which case the function returns the step count and a result indicating the target is not in the list, while always shrinking the search interval efficiently. We begin by creating a sorted list of numbers that act as book identifiers in a digital library. Using a range of values from 0 up to, but not including, 1024, we generate a sequence and convert it into a list. This gives us an ordered collection of items that will serve as the basis for demonstrating how binary search algorithms work later in the script. We choose a target value near the upper end of the list, such as 1000, to show how the search interval shrinks during the algorithm. Using a value close to the end highlights how the method handles large ranges. It also lets us see how a safe midpoint calculation keeps the search both efficient and accurate as it narrows down to the target. We first run a basic binary search on the list of book IDs and a target ID, where the algorithm repeatedly halves the search range but may not always shrink that range correctly. Then we run a safer version of binary search on the same data, which guarantees the search interval is reduced properly and avoids infinite loops or wrong results. Each version reports how many steps it took and the position of the target if it was found. By comparing these outputs, we can evaluate both the efficiency and the reliability of the two approaches. We compare the naive and safe versions of binary search by printing how many steps each one takes and which position they find. This shows how the naive approach behaves in terms of efficiency and accuracy. We then look at the safe version, which preserves the correct logarithmic growth in the number of steps. Finally, we compare both results to the list length and the theoretical ideal of about 10 steps, illustrating why using a safe midpoint calculation is important for optimal performance. This script compares a naive and a safe way to compute midpoints in a binary search. The naive version averages the low and high indices, which can cause the midpoint to stop changing and lead to infinite loops or missed results. The safe version instead adds the low index to half the distance between high and low, so the search interval always shrinks correctly. Both methods are used to search for a target book identifier in a sorted list, but the naive search may take extra steps or fail, while the safe search reliably finds the target in a logarithmic number of steps. The output reports how many steps each method takes and where the target is found, showing that the safe approach is more efficient and dependable. Iterative versus recursive search. Binary search can be implemented either iteratively or recursively, but both follow the same idea. Focus on the middle of the current range, decide if the target is to the left or right, and then continue searching only in that half. In a recursive version, the function calls itself on smaller portions of the data, while in an iterative version, a loop updates the search boundaries. Both approaches have the same time complexity, where the number of comparisons grows logarithmically with the size of the input. This makes binary search much faster than scanning through every element in order, as long as the data is sorted. The choice between recursion and iteration mainly affects coding style, not the fundamental efficiency of the algorithm. Iterative and recursive binary search have the same logarithmic time complexity, but they behave differently in practice as input size grows. Recursive binary search relies on the call stack and creates a new stack frame for each call, which can be problematic when stack memory is limited. In contrast, iterative binary search uses a loop and a fixed set of variables, so its memory usage stays constant. Because of this, iterative binary search is often preferred in systems where memory efficiency is especially important. When choosing between iterative and recursive binary search, focus on how they affect performance in practice. Both make the same number of comparisons, but recursion adds some overhead, which can slightly slow things down in very performance-critical cases with many searches. The most important point, however, is the algorithm itself. Linear search time grows directly with the number of elements, while binary search time grows much more slowly, with the logarithm of that number. The choice between iterative and recursive versions mainly changes implementation details and memory usage, not the fundamental efficiency of the search. Python code, iterative versus recursive search. We want to compare the performance of iterative and recursive versions of binary search in a simple way. Both approaches should show the same logarithmic growth in running time as the list size increases. To make this clear, we will measure and print how many steps each version takes for different list sizes. This lets us see that, despite their different implementations, both forms of binary search scale in essentially the same efficient way. The commented line mentions installing NumPy, Matplotlib, and Seaborn, but also notes that these libraries are not required to run this script. This means the script is self-contained and does not depend on external packages for its main behavior. Its purpose is to demonstrate binary search algorithms on their own, without adding extra library dependencies. As a result, you can focus on understanding the binary search logic without needing to set up additional tools. In this version of iterative binary search, we also count how many steps the algorithm takes. We start with a left index at the beginning of the list, a right index at the end, and a step counter set to 0. While the left index is less than or equal to the right index, we increase the step counter, compute the middle position, and compare the middle element to the target. If the middle element matches the target, we return the number of steps taken. If the middle element is smaller than the target, we move the left index just to the right of the middle. Otherwise, we move the right index just to the left of the middle. If the loop finishes without finding the target, we return the total number of steps performed. This helper function performs a recursive binary search while counting how many steps the search takes. It works on a sorted list using a target value, current left and right positions, and a step counter. If the left position goes beyond the right, the search space is empty and it returns the number of steps taken. Otherwise, it increases the step counter, finds the middle position, and compares that element to the target. If the middle element matches the target, it returns the current step count. If it is smaller, it searches the right half, and if it is larger, it searches the left half, continuing this process recursively. This function serves as a simple, user-friendly way to run a recursive binary search on a sorted list. The user provides the list and the target value, and the function then calls a helper that handles the recursive steps. It initializes the search by setting the left index to the start of the list, the right index to the end, and the step counter to 0. This design keeps the interface clean for the user while delegating the detailed recursive logic to the helper function. We will use sorted lists of 4 different lengths: 16, 32, 64, and 128 elements, to study how binary search performs. These specific sizes let us see how the number of search steps grows as the list gets larger. By applying both iterative and recursive versions of binary search to these lists, we can clearly compare how each approach scales with list size. We choose a target value of 42 because it is guaranteed to appear in all the lists we search. This ensures that both the iterative and recursive versions of binary search will always find the target. By doing this, we can focus on comparing their performance without worrying about cases where the target is missing. The code first prints a header line that labels the output columns as size, iterative steps, and recursive steps. This header describes the results that will follow and clarifies what each column represents. By doing this, it creates a clear format for showing how many steps each search method takes for different list sizes. As a result, it becomes easy to compare the performance of the iterative and recursive approaches. We examine how iterative and recursive binary search perform on lists of different sizes. For each predefined size, We build a sorted list of numbers starting at 0 and ending just before that size. We then search this list for the target value 42 using an iterative binary search and count how many steps it takes. We repeat the search with a recursive version and count its steps as well. Finally, we output the list size along with the step counts for both methods so we can directly compare their performance. This script compares iterative and recursive versions of binary search by counting how many steps each needs to find a target value in sorted lists of different sizes. Both search methods return the number of steps required to locate the target, which is set to 42. The program tests lists that grow from 16 up to 128 elements and prints the list size with the corresponding step counts. The results show that both approaches have logarithmic time complexity, meaning the number of steps increases slowly as the list size grows, demonstrating their efficiency for searching sorted data. Testing binary searches. Boundary edge cases. When testing a binary search, pay special attention to boundary edge cases where subtle bugs often appear. These include searching for the first and last elements and handling very small search intervals with only 1 or 2 items. Algorithms may work correctly for middle values, but fail at the edges or get stuck in infinite loops. To prevent this, design tests that specifically target the smallest and largest values in a sorted list and use them as stress tests to catch off-by-one errors and incorrect loop conditions before they affect real applications. When implementing binary search, it is important to verify that the logic works correctly on very small lists, such as those with 0, 1, or 2 elements. Bugs often appear only when the search interval is tiny, because index updates can accidentally skip valid positions or stop the search too early. This can lead to incorrect results, like reporting that an item is missing from a catalog that contains only that one item. By systematically testing both successful and unsuccessful searches on these small cases, you can confirm that your binary search handles all input sizes, not just large arrays. When implementing binary search, you must handle index limits and updates carefully, especially with large datasets. Errors in computing the midpoint can cause integer overflow or skip valid positions, and inconsistent updates to the low and high boundaries can leave some indices unchecked. These problems are most likely when the target is near the midpoint at the current low or high index, or when the search range has shrunk to a single element. Including these boundary situations in your tests helps ensure the binary search works correctly for different data sizes and target positions. Python code, boundary edge cases. Use simple tests to explore how binary search behaves at its boundaries, focusing on tiny lists and values at extreme positions. These edge cases often expose subtle bugs that do not appear with larger, more typical inputs. By comparing the results of a buggy search implementation with a correct one on these boundary scenarios, you can clearly see where the logic fails. Standard library tools are enough for these tests, so no special installation is required. This example describes a binary search function that contains a deliberate bug. The function keeps 2 pointers at the start and end of a list and repeatedly checks the middle element, moving the lower pointer up when the middle value is less than the target, and the upper pointer down when it is greater. If it finds the target, it returns the middle index. If the loop finishes without a match, it returns -1. The bug is in the loop condition, which stops when the lower and upper pointers become equal, but it should continue to allow them to be equal so that all boundary positions are correctly checked. A correct binary search function works by keeping 2 pointers at the start and end of a sorted list and repeatedly checking the middle element. While the start pointer is less than or equal to the end pointer, it finds the middle index using integer division. If the middle element equals the target, it returns that index. If the middle element is less than the target, it moves the start pointer just above the middle to search the upper half. If it is greater, it moves the end pointer just below the middle to search the lower half. If the loop finishes without a match, the function returns -1 to indicate the target is not in the list. The code creates a small set of arrays to test boundary cases in binary search algorithms. These arrays include an empty list, a list with 1 element, a list with 2 elements, and a list with 3 elements. By using such minimal and varied data, the tests check how the search behaves at the beginning and end of the lists and when the target value is missing. This helps ensure the binary search functions handle edge cases correctly. The code defines a small set of target values, such as 1, 4, 7, and 9, to test different situations in the binary search functions. These targets are chosen so that some may appear near the beginning or end of a list, while others may not appear at all. This selection helps check how the search functions handle edge cases and boundary conditions. Using these targets ensures that both the buggy and the correct versions of the search are thoroughly evaluated. We test the buggy binary search by running it on each small list and each target value, and then compare its result to the result from a known correct binary search. For every combination of list and target, we record both outputs and check whether they match. Whenever the 2 results differ, we print the list, the target, and both outputs. This process reveals exactly which cases expose the bug, helping us spot boundary problems in the faulty search implementation. This script compares a faulty binary search with a correct one by running them on small lists designed to expose boundary edge cases. The buggy version fails when the target value is at the edges of the list or missing entirely, while the correct version handles these situations properly. For each target in each list, the script checks both search results and reports any differences, including the list, the target, and the 2 outcomes. This makes it clear how small, logical mistakes in binary search can produce wrong answers, especially in tricky edge cases. Handling duplicates and absence. When testing a binary search, it is important to consider arrays that contain duplicate values, since real data often includes repeats. A standard binary search may return any matching index, but some applications require a specific one, such as the first occurrence. Your tests should therefore check not only that the target is found, but that the correct index among the duplicates is returned. They should also confirm that the algorithm does not get stuck in an endless loop when the middle element keeps matching the target. When testing binary search, you must check how it behaves when the target value is not in the array. A frequent bug is that the search returns a nearby index instead of clearly signaling that the target was not found, often due to how the loop ends or how the final return value is chosen. To avoid this, test with targets that are smaller than all elements, larger than all elements, and between existing values, and confirm that the function consistently reports that the target is missing, rather than returning a close but incorrect position. When testing binary search, it is important to include cases with duplicate values and missing targets, because these can expose subtle bugs. For example, if you search a sorted list for a value that is not present, a flawed implementation might incorrectly return a nearby duplicate due to bad comparison logic. If you modify binary search to return insertion positions, you must compute the index correctly when the target is absent so the ordering remains stable. These kinds of tests help uncover off-by-one mistakes and boundary errors, leading to more predictable behavior across different data patterns. Python code, handling duplicates and absence. This material should clearly demonstrate how binary search behaves when there are duplicate values and when the target is missing. It needs to show how to correctly find the first occurrence of a value and how to handle the case when the value is not found at all, using simple, beginner-friendly examples. The focus is on helping learners understand common off-by-one mistakes and equality comparison issues that often appear in binary search implementations. Only standard libraries are needed, so no special installation is required. In binary search, we define a function that returns the index of a matching value in a sorted list, or -1 if the value is not found. We keep 2 pointers, left and right, marking the current search range, starting at the first and last positions in the list. While left is less than or equal to right, we compute the middle index, check the value there, and compare it to the target. If the middle value equals the target, we return that index. If it is less than the target, we move the left pointer just to the right of the middle. If it is greater, we move the right pointer just to the left of the middle. If the loop ends without a match, we return -1 to indicate the target is not in the list. This function uses binary search to find the first occurrence of a target value in a sorted list. It keeps track of left and right pointers and a result index, which starts at -1 to indicate that the target has not been found. In each step, it checks the middle element. If it equals the target, it records that index and then continues searching to the left to find an earlier match. If it is less than the target, it searches the right half. If it is greater, it searches the left half. When the search finishes, it returns the stored index, which is either the first position of the target or -1 if the target does not appear in the list. We use a sorted list called readings list that contains the numbers 10, 20, 20, 20, 30, 40, and 50, including some duplicates. This list serves as a simple dataset for demonstrating how binary search works. It lets us see how binary search handles repeated values and how it locates specific numbers within an ordered sequence. We set the target value to 20 and use a binary search function on a sorted list to find any one index where this value appears. This basic search stops as soon as it finds a match and returns that index. We then use a second version of binary search that is designed to find the first occurrence of the target. This version keeps searching even after finding a match, so it can return the index of the earliest instance of 20. Comparing the results of these two searches shows how the list handles duplicate values by producing different indices for the same target. In this example, we choose a target value of 5 that is smaller than every element in a sorted list to test how the binary search for the first occurrence behaves when the target is missing. We run the search on the list using this target, and the function attempts to find it. Because 5 does not appear in the list, the function returns -1. This shows that the search correctly indicates when a target is smaller than all list elements and not present at all. We set the target value to 60, which does not appear in the sorted list of readings, and then call the binary search function that finds the first occurrence of a target. The function searches through the list for 60 but does not find it. As a result, it returns -1 to indicate that the target value is not present in the list. We begin by printing the list with duplicate values to give context for the search results. We then show how the first binary search function returns the index of some occurrence of the number 20, proving it can find a target even when it appears multiple times. Next, we use the second function to return the index of the first occurrence of 20, demonstrating that it can specifically locate the earliest position among duplicates. Finally, we search for the numbers 5 and 60, which are not in the list, and see that the function correctly returns -1 for values that are missing or outside the list's range. This script demonstrates how binary search works on a sorted list that may contain duplicates. It uses one function that returns any index where the target value appears, and another that specifically returns the index of the first occurrence among duplicates. When searching for a value like 20, the first function may return any matching position, while the second always returns the earliest one. If the target is not in the list, such as 5 or 60, both searches return -1 to indicate it was not found. Overall, the example shows how binary search can handle duplicates and missing values, and helps reveal common, off by 1, and equality comparison errors. PyTest-based verification. To check that a binary search function is correct, it is better to use an automated test framework like PyTest than to rely on manual checks. With PyTest, you can write small tests that automatically cover key situations, such as when the target value is present, missing, or appears more than once. Running these tests helps quickly reveal errors, including subtle off-by-1 mistakes. This systematic testing approach improves reliability and mirrors how engineers validate search routines under many different data conditions. PyTest's parameterized tests let you check a binary search function by running one test over many input and output combinations. You can easily cover lists of different lengths, including empty and single-element lists, and targets that are present or absent. This systematic coverage helps reveal consistent mistakes, such as wrong index values or missed targets. Using this approach makes it easier to catch subtle bugs and improves the reliability of binary search in real-world tasks, like searching logs or catalogs. With PyTest, you can verify that your binary search works correctly in tricky situations, such as when the data contains duplicates or when the target value is missing. You should write tests that check whether it returns the correct index when duplicates appear, and that it clearly signals when the target is not found, either through a special result or an exception. Running these tests regularly helps you quickly catch bugs introduced by changes or optimizations. This approach supports a defensive programming mindset, similar to the rigorous testing used in safety-critical engineering fields to maintain reliability. Python code, PyTest-based verification. This segment will demonstrate how to verify the correctness of a binary search implementation using a PyTest-style approach. We will show a simple binary search function that intentionally contains a boundary error. Then run manual checks that mimic PyTest behavior. The program will print clear pass or fail messages for each test so you can see how the bug affects the results. In real projects, you would install and use the PyTest library to run these tests automatically. This function is meant to perform a binary search on a sorted list, starting with the left index at 0 and the right index at the last position, then repeatedly checking the middle element and narrowing the search to either the left or right half. If the middle value equals the target, it returns that index. If the middle value is less than the target, it moves the left index to just after the middle. Otherwise, it moves the right index to just before the middle. After the loop, it checks whether the remaining position holds the target and returns that index if it does, or -1 if the target is not found. The deliberate bug is in the loop condition, which stops when the left index equals the right index, so the final element may never be checked. The condition should allow the left and right indices to be equal to ensure every element is examined. To understand correct binary search behavior, we define a function that searches within a sorted list using two bounds, a left index starting at 0 and a right index at the last position. While the left index is less than or equal to the right index, we compute the middle index as the integer average of left and right. Then compare the list value at this middle position to the target. If the middle value equals the target, we return the middle index. If the middle value is less than the target, we move the left index to one position right of the middle to search the upper half. Otherwise, we move the right index to one position left of the middle to search the lower half. If the loop ends without a match, we return -1 to indicate the target is not in the list. We define several test cases to check that a binary search function works correctly on a sorted list of numbers. Each test case is a tuple containing a sorted list, a target value to search for, and the expected index of that target. The cases include finding 1 at index 0 and 9 at index 4 in a list of odd numbers, confirming that a missing value like 4 returns -1, and verifying that searching any value in an empty list also returns -1. Another case uses a list where every element is the number 2 and expects the target 2 to be found at index 0. Together, These tests cover typical situations and edge cases to ensure the search behaves as expected. We create an empty list to store any test cases that fail, then loop through each case, which provides a data list, a target value, and the expected index. For each case, we run the buggy binary search function with the data and target to get a result index. Then compare it to the expected index. If they do not match, we record the data, target, expected index, and actual result in the failed cases list. This manual process imitates how a testing framework would run parameterized tests and helps us check how the function behaves. We begin by reporting how many tests were run in total, using the length of the list of test cases to show how many scenarios were checked. We then report how many of those tests failed, based on the length of the list of failed cases, which gives a quick sense of the function's reliability. For each failed test, we unpack the input data, the target value, the expected index, and the actual index returned, and print these details. This information makes it clear exactly what input caused the failure, what result was expected, and what the function actually produced. To verify that the correct binary search implementation works, we run it on a series of test cases and compare its output to the expected index for each one. A generator expression produces these comparisons, and the all function checks that every comparison is true. If all tests pass, we print a message confirming that the correct implementation succeeds on every case, giving us confidence in its accuracy. This material describes a script that compares a buggy binary search implementation with a correct one by running a series of manual tests, similar to those in PyTest. It checks whether the buggy version returns the expected index for different inputs and reveals that the error appears when the target value is at the boundary of the list. The script reports how many tests were run, which ones failed, and details about each failure. It then shows that the correct implementation passes all tests, illustrating how a small logic mistake can cause incorrect results and underscoring the need for thorough testing. In this lecture, you learn to implement linear and binary search algorithms correctly in Python, compare the time complexity of linear and binary search and relate it to input size and ordering, and identify and avoid common implementation errors in binary search code. In the next lecture, Lecture B, we will go over Pythonic searching.
Thank you for your attention. See you all in the next lecture.